Hi. Hi, Margaret.
Hi.
All right, we can have a conversation.
Oh, gosh.
I tell you what I'm gonna do. Well, I've still got you on the phone.
Okay. I'll stand over here.
Okay. Well, it's a great honor to introduce the first keynote and presidential keynote of our 17th president, Professor Bob Hariri, a serial entrepreneur and also a visionary leader. And it's a great honor to have Dr. Hariri speak about the stem cell. Dr. Hariri.
Thank you. Thank you, Babak. Really privileged to be here. So what I'd like to try and do today is introduce you to what I believe the future of cellular medicine and what we call functional regeneration is for the medical field in general, but try and give you some specifics that are relevant to the neuroscience area. As a company that is right on the brink of going from a private to a public enterprise, I bring your attention to this statement because some of what I'll speak about encompasses work that is ongoing at our company, and therefore there are certain compliance requirements. Just to kind of ground everybody, I think everyone in this room obviously knows what stem cells are. They are cells that retain the versatility to replicate and make identical copies of themselves, which retain all of the same properties, as well as differentiate and specialize into all of the different unique cell types of every organ and tissue in the body. Cellular therapy and beyond cellular therapy involves the augmenting or replenishing a reservoir of stem and immune cells that can actually function to restore certain activities and functions necessary for both the ongoing repair, renovation, renewal, but also in order to provide defense and combat any disease or injury. This is largely linked to stem cells' unique ability to provide the access to the full synthetic repertoire of every cell in the body. And I'm going to get to more detail about that in a moment. Now, many, many years ago, when I was a faculty member at Cornell University Medical College, I became very interested in the field of stem cells because as a doctor who was heavily involved in the research and treatment of patients with traumatic brain injuries, I was convinced that this emerging field may hold the key to unlocking some of the regenerative ability of the brain that would help restore functionality in severely injured patients. This photograph of fetal surgery was one of the early observations I had that resident in the gestational window where the developing fetus is still connected to this remarkable organ, the placenta, it retains a remarkable regenerative power. And if that regenerative power could be harnessed, it could in fact play a big role in the treatment of neurologic injuries. Now, I have had the pleasure in my life of working with some of the great pioneers in health and basic science, including Dr. Craig Venter. And one thing that Craig, as a partner of mine, taught me was that every cell has resident in its nucleus a system of biological software that is encoded in our DNA. And that DNA actually acts much like a programming language. And that programming language is interpreted and processed in the cytoplasm of every cell, and the outputs of that processing gives rise to the secreted products as well as the products that are resident in the cell, including the surface of the cell. So if you think about it, I'd like you to consider the fact that every stem cell is like a tiny computer with a master boot disk which resides inside the nucleus of that cell. And what that means is that just like in your computer, when your software gets corrupted, there may in fact be an opportunity to reprogram, correct, or reboot that. Now, one of the other observations we made early on was that there is clearly a change in the quality and quantity of stem cells that are resident in every organ and tissue of the body with age. This graph, data that first came out of Scotland, inspired me to look a little bit deeper, and what we found was that this correlation was very, very tight. Just to put it in perspective, a newborn, if you look at the bone marrow of a newborn, roughly one in every 30,000 cells in the bone marrow of a newborn is a stem cell. But if you look at the bone marrow of an 80-year-old, it drops down to 1 in 30 million. And so that 1,000-fold decline in the stem cell concentration, if you will, has significant impacts on that individual's ability to respond to injury and disease. This actually was confirmed in studies we did with animals where we looked at tissues as a function of age, muscle, brain, bone, and we found that there was in fact this very, very predictable decline in the number of cells capable of having that stem-like function with age, and it correlated to a decline in functionality. We actually tested this many years ago in animals where we were able to recover stem cells from the placenta, store them away in cryopreservation, and give them back to animals as they aged. And this early kind of preliminary work inspired me to look deeper at how stem cells could be used to restore performance and function during aging, but also in response to disease. And what you see here is that animals who received their own stem cells back after they reached sexual maturity lived on average 40% longer than their litter mates. Very interesting observation. So if you think about it, those physioanatomic changes that occur with age really reflect the continuous renovation of tissues with stem cell reservoirs that have to be maintained in high quality. Corruption of that reservoir results in a less than perfect, less than ideal renovation process. Now, at the companies that I've built over the last 20 years, focused on harnessing the unique biological properties and the ready availability of this organ, the postpartum placenta. As you know, it's biological waste material that occurs at the end of every full-term pregnancy. I recognized early on that this was the ideal platform to develop therapeutics. Readily available, can be procured under very, very rigorous conditions, can be quality controlled to ensure that the biological properties necessary as therapeutics would in fact be resident in every byproduct, and incredibly, incredibly scalable and economical. You know, one of the challenges in developing any breakthrough therapeutic isn't just showing on the bench that it works and showing in a small number of patients in the clinical trial that it works. If you can't demonstrate that you can actually scale this to disseminate to the broad population, I think you're expending a lot of energy perhaps in the wrong direction. I was convinced early on that for stem cells to have a meaningful role in medicine, people were going to have to develop them and productize them much the way we productize pharmaceuticals. And what that meant, it meant that this had to be done in an industry environment. I very much enjoy my academic history. I rejoined my faculty at Cornell as an adjunct professor of neurosurgery, and it's great to be among some of the most brilliant minds active scientifically and clinically. But in order to come up with solutions for diseases with therapeutic products, one has to take this into an industrial environment. I was very fortunate. Back in 1998, 1999, I decided that I was going to interrogate the postpartum placenta, the biological garbage, if you will, that occurs after a full-term healthy pregnancy that hospitals pay to get rid of. And I decided to interrogate that organ to see if, in fact, my thesis was correct, that it was a factory for the production of stem cells that could be recovered under very, very tight controls and turned into therapeutic products. In order to do that, my company was very fortunate to have merged into an emerging biotechnology leader called Celgene Corporation. And at Celgene, we built a company that amassed a market capitalization of almost $120 billion, and we were able to reinvest much of that money in creating the best systems and the best infrastructure to turn living cells into medicines, and that's illustrated in this slide here. Now, I want to talk about the various opportunities that exist for us. One of them is to look at the stem cell population, the fundamental stem cell population of the placenta, and what about it is unique and potentially useful as therapeutics. So let's talk about a couple of the properties of cells from the placenta. If you think about it, the placenta is nature's professional universal donor tissue. Okay? A placenta which is produced by the developing fetus has the genomics of the developing fetus. Therefore, it is only 50% a perfect match to the mother that carries it without inducing any immunologic conflict. In fact, if you think about it, even in surrogate pregnancy, when the mother is not even related to the fetus or its placenta, she does not mount an immune response against that fetus or placenta, and vice versa. She is tolerated by that developing newborn. This means that the cells from that organ potentially have the ability to be a one-size-fits-all product. Now, many of you know that in organ transplantation and stem cell transplantation, the burden on the practitioner is to find a perfect match between the recipient, the intended recipient, and a donor. That's not easy. We know that, right? That's why you have things like the Network for Organ Sharing, the National Marrow Donor Program, and so on. But if we had products that in fact were one size fits all, think about what that would mean. It means that you could inventory these cells at therapeutic locations and deliver them without the need to do any fancy analytics or diagnostics, but in fact be assured that every possible recipient has access to a product. The first thing we identified early on was that placental adherent stem cells, what we mean by adherent means that they're sticky. Those cells are very, very good at modulating the immune system and also driving pro-regenerative activities. And the great part about it is that from one placenta, we can harvest so many of these pluripotent, meaning very versatile stem cells. And these cells give rise to enormous, enormous numbers of progeny. To put this in perspective, from a single placenta, we can produce hundreds of thousands of 100 to 200 million cell doses from a single placenta. If you think about that, hundreds of thousands of doses from one organ, that is really, that's music to the ears of someone wanting to develop a therapeutic. Now, to do this is a relatively complicated process, and we spent 20 years perfecting it. First and foremost, you have to have systems to procure these organs under very, very tight controls. You've got to have quality systems. You've got to procure under full informed consent. You've got to be able to screen the contributing parental, maternal, and paternal medical histories, and you have to do it in a system that delivers you the raw material under very, very tight controls reliably. Now, to do that, the procurement process means you've got to screen donors, and then you've got to get that organ to your laboratory. For those of you who are squeamish, I'm going to short circuit this video, but that's how a placenta arrives in our laboratory, and it is first evaluated to see whether or not it qualifies for the next steps in processing, which involves the evaluation of whether or not it meets the clinical grade for production. And here, our technicians and engineers do that by analyzing components of the product as well as testing things like blood for infectious agents and so on and so forth. And then we have to take this and we've got to actually derivatize it so that we can turn it into products. That involves mechanical processes like dissection, mechanical and enzymatic digestion, and that yields individual cells that can be taken and create what we call a master cell bank, and from that master cell bank we can produce large quantities of finished product. And that involves establishing cultures in the form of cell lines, which can then go on to be mass-produced in bioreactors and cell factories, and this is what we call culture expansion. That's what gets us from one placenta into millions of doses. And these are just videos from our laboratories at Cellularity where we do this dozens of times every day. Now, I was very impressed early on with some of the observations I made about the immunomodulatory and regenerative potential properties resident in placental cells, and some of our publications have demonstrated clearly that this is a native characteristic of these cells. And if you think about it, let's look at just the immunomodulatory behavior of the placenta. We know today that many pregnant women who have autoimmune diseases during pregnancy will actually go into durable remissions. We believed early on, we theorized early on that this was related to the fact that placental cells could in fact downregulate some of the immune responses that led to that autoimmune disease. So what did we do? We went and tested it, and sure enough, that's actually to be an opportunity for us to treat patients. We've treated a number of autoimmune diseases and have seen profound clinical responses with those products. But what about relating this to an area that's of interest to all of us, which is the neurologic diseases? So some of the data that you're seeing here is the fact that we demonstrated that these cells, in their native form, when administered by intravenous infusion, actually downregulate inflammatory responses and can promote some of the regenerative responses necessary to go from a damaged, vulnerable cell and tissue to a normally functioning cell and tissue. And these effects can be seen not just with anti-inflammatory activity, but also being able to stimulate some of the regenerative processes necessary for damaged, vulnerable neurons, for example, to repopulate an injured brain. We also showed that although this is great basic biology, that this basic biology in fact translates into improvement in functional properties in animals. And for example, in this data, you can see that in models of stroke, where the brain is damaged by cutting off the blood supply, we can actually statistically significantly improve functionality by using these same cells infused intravenously after those injuries have occurred. We also show that there's a protective effect of these cells, and they can actually decrease apoptosis in the injury site in a variety of injury models. And this means that the window of opportunity to deploy these products appears to be very broad, from early after the onset of injury well through the process of recovery. And we believe that there may even be longer-term applications, because these same placental stem cells, through their secretome and products that are released as a consequence of their use as a therapeutic, can actually increase the proliferation and neurogenesis that occurs in the brain. And this may in fact even improve cognitive performance in the aging population. You will be hearing a great deal about Alzheimer's disease today. One of the great challenges going forward, because of the prediction that Alzheimer's may impact such a large percentage of our population that we have to deal with it aggressively, it's very possible that regular cell therapy with products from the placenta may in fact stimulate processes that preserve cognitive function over prolonged periods of time. We also showed that in models of, for example, Parkinson's disease, where a very, very discrete and specific injury that's occurring to part of the synthetic system of the brain that's responsible for producing the neurotransmitters that control things like movement actually can be ablated or attenuated with the administration of these cells as seen here. And the profound significance of this data, even in vitro systems, leads us to consider that this may be a very important area for us to test clinically. We also know that these cells can stimulate through their secretome an improvement in the cellular functions that are necessary for the packaging and secretion of their own synthetic products, like neurotransmitters. So alpha-synuclein is an example of that. And then we also demonstrated that in models of autoimmune neurologic disorder, experimental autoimmune encephalomyelitis is a model for multiple sclerosis. We profoundly reduced the effects of that autoimmune destruction of important cells in the brain that may in fact be therapeutically valuable in treating the symptoms and potentially arresting progress in that autoimmune disease. We have in fact, we've generated some clinical data in humans that supports this concept, and it's our objective going forward in large part because of the work going on here at the Society to find ways to fund ever more accelerated and active clinical research in this area. But then there's even more that comes out of the placenta, more than I can even speak to you in the limited amount of time I've got on stage here. But if you think about it, the placenta is a source not just of cells, but also biological materials. If you go into the exhibitor hall, you'll see our company has a booth where you can see some of the products that are currently available clinically and available commercially, which can be applicable to the treatment of a number of disorders, including neurologic disorders, spine disorders, and so on. But there's a new area of investigation we're very active in, which is to take the packaged communication tools of these stem cells, exosomes, and an exosome is a very, very tiny membrane-bound vesicular-like structure that packages a variety of important signaling molecules, growth factors, and microRNAs. We've developed technologies to produce these at very, very high scale, high quantity, and high quality. And the reason this is important, again, as I mentioned before, a therapeutic is only as valuable as its deployability. Deployability is dictated by safety, obviously, and it's also dictated by scale and economics. Some of the great breakthroughs in cellular medicine, as you know, specifically in immuno-oncology, treating cancer with immune cells, although remarkably important and an incredible proof of concept, the price tag associated with something like chimeric antigen receptor engineered T cells at $500,000 per therapy is clearly not sustainable in our healthcare system or any. However, exosomes can be produced at enormously attractive economics. In fact, probably economics that rival, if not exceed that of traditional pharmaceuticals. We know that our exosomes from the placenta contain tens of thousands of proteins, including a number of pro-neurogenic proteins. We know that these exosomes can also deliver thousands of unique microRNAs that can regulate cell functions and can affect cells both epigenetically and in improving things like transcriptive behavior. And in vitro demonstrations, we can show that the pro-angiogenic activity of the payloads of these exosomes actually improve and promote migration of endothelial cells, which are central to the reconstitution of functionality in an injured brain. If you think about it, what is the endothelial cell? It is the gatekeeper to every tissue and organ in our body. And in order for for cells and also other therapeutics to make their way into these organs, you need to have products that can also interact with that gatekeeper. We also can show that the byproducts and the payloads of placental exosomes can actually influence the behavior and migration of things like astrocytes in the brain. Also very, very important as a potential tool to use in therapeutics. And the pro-neurogenic activity has been demonstrated in models of stroke in animals. And as you can see from this data, we are replicating some of the important benefits that can be conferred by a placental stem cell being delivered as a therapeutic just by using their communications tool, the exosome. So think about where the future is headed when you have in your clinical tool chest cells that have biological activity. You've got biomaterials that are useful in reassembling and reconstituting this organ. And then you have a extremely safe, extremely economical byproduct in the form of exosomes that can help you tune, if you will, some of the functions of those cells. So if you think about it, we want to have therapeutics that can immediately intervene and arrest the disease process, begin to stimulate repair, and then can be tuned to optimize the clinical effect. Because no two patients are the same, no two diseases are the same, no two injuries are the same. This is what we do at Cellularity. The thing which probably I find most exciting for myself as I get more and more gray in my beard is that the neurogenic, the pro-neurogenic activity of these exosomes can dramatically improve the cellularity and functionality of parts of the brain necessary to preserve cognitive and motor performance. That gives guys like me hope. So the data that is exciting and also suggests that these products will be useful in a much broader array of clinical conditions. We've demonstrated that exosomes, just by simple intravenous administration of an innocuous, highly safe product, can stimulate angiogenesis and help create new collateral circulation in compromised organs and tissues. We've done this in a profound number of ways, and by the way, this activity appears to echo what happens when we administer placental-derived stem cells into, for example, peripheral artery disease that leads to non-healing wounds. This is extremely exciting as a surgeon. If I had a tool 20, 30 years ago that I could inject that would turn an old, degenerated vascular system into a new set of highways to improve circulation, I would be using it all the time. I'd probably take a lot of it home, too. So the opportunities that are relevant in neuroscience that I've been speaking about include our activities in oncology, and I'll be speaking later in the conference about that. Among all the things the placenta gives rise to, I can take those stem cells from the placenta and I can produce immune cells. Among those cells are natural killer cells, and we are active in the clinic today in a number of solid tumors and hematologic malignancies where we're showing that the fundamental function of the placental immune system as a defense system to protect that fetus at all costs actually has therapeutic value as an independent tool to control cancer in independent diseases. As Dr. Khattab had mentioned, we were the first group to have an FDA-filed IND to treat COVID with placental-derived cells. And those cells were natural killer cells. And it turns out, if you think about it, right, nature's a lot smarter than we are. And the placenta has evolved to defend the developing fetus at all costs. If you think about it, human beings and the average lifespan of a human during evolution averaged about 25 to 30 years of age. That means there's a limited window for procreation. If you think about it, a human being devotes 9 months of reproductive energy generally to one offspring. Okay? In order to maintain the population and continue to repopulate, you have to protect that fetus at all costs. And among the properties that I've mentioned, the immunologic properties, but also the defense properties, defense against infectious diseases, and even defense against cancer, means that this organ has evolved properties that are potentially of enormous value for us in treating other diseases. So in summary, the current state of play in this field, and I apologize, it's a brief presentation. There's a lot going on. As I mentioned before, Cellularity, the first spin-off company of one of the most successful biotechs in history, is literally a week away from trading as a publicly traded company on NASDAQ. And so, thank you. It's largely responsible for the bags under my eyes. But the fact is that we have products that include cells, biomaterials, exosomes, highly versatile products that are going to be used to help control the immune system, stimulate regeneration, and ultimately, I believe, where I want to take this is to use it to preserve for the preservation of human performance. So as I leave you, I want to just say this. A lot of things we're talking about are important to deal with. We talked a little bit about how important Alzheimer's is, and you're going to be hearing more about that. Preservation of cognitive performance is among the most important things we need to be thinking about in our aging population. If you consider preservation of high-performance mobility, preservation of high-performance cognitive function, preservation of high-performance immunity, and, selfishly, preservation of youthful aesthetics, will make every year we add to people's lives worth living. And that's part of the mission at Cellularity. So thank you very much for your attention.